Welcome everybody. Here is your second lesson for the second day of class, a lesson on 2-4 rates of change and tangent lines. One of the beginnings of actually moving away from pre-calculus limits into calculus, tangent lines and slope of the tangent lines. A couple quick little refreshers as we go back to our geometry days. This is a visual of different types of key vocabulary words you would have used in geometry class. The two things we're going to be using here that are the most important things are secant lines and tangent lines. Now this is on a circle, but we're really not going to be talking about a circle. We're going to be talking about a function. Let's make up a quick little function. If I'm going to give you a secant line on this function, the secant in a circle, a secant line, will intersect the circle at 2 points. So a secant line on a function will intersect the function at 2 or more points. So that's a secant line. And a tangent line here in the circle just nicks that circle at 1 point, and a tangent line on a function just nicks that function at 1 point. Now if you continue this on, I will hit it again, but we're really talking about local tangency. So this is like the local area, and you're going to hear that word a lot when we talk about local linearity. So there's a lot of work here that I have you do if you were in class, but let me give you a quick little example. This, by the way, mirrors a lot of what we discussed last class. So if I wanted to calculate a slope, we can't really calculate the slope between the two same points. So if I wanted to calculate a slope at point 1, 1, I couldn't do that because from these 2 points, 1, 1 to 1, 1, they're the same point, and if you do the slope, you get 0 over 0. So the way to do that is to approximate it by looking at different secant lines. So if I wanted to go from 1, 1 to 4, 16, and why am I using these special numbers? Because this is the function I'm using, y equals x squared. Why am I using 1, 1? Because if I plug a 1 in for x, the output is 1. If I plug a 4 in for x, the output is 16. 4 squared is 16. So that's why I'm using this specific function, which is a parabola opening up, but I'm only looking at the first quadrant. Now, I'm going to try to do this on the smartboard. It's not going to be a perfectly straight line, but what I'm doing is I'm calculating the slope of that blue line. So, I would normally put this on the board, but I'm not going to do that for you. But here you go, the slope of that approximate line I drew before, which is now a little bit better drawn digitally in red, has a slope of 5. But my goal is I want the slope of the tangent line, which just nicks this function at 1, 1. So if you are good at drawing tangent lines, you kind of be able to just nick it right there. And if you can see that red line I just drew in doesn't seem to have a slope of 5 because the other digital red line has a slope of 5, and this is less steep. So it's got to be less than 5. So instead of doing it from 1, 1 to 4, 16, what happens if I go from 1, 1 to 3, 9? Well, then I could just do the same calculations for slope. y2 minus y1 over x2 minus x1, and this little delta stands for change in y over change in x. I get 4. Well, that's this second red line that's in here, kind of on the inside there. I bet I could even get a better approximation of the slope of the tangent line by going to the next integer over. So from 1 to 2. I bet I could do pretty good of that estimated tangent line. And then I get 3. Here's the mathematics behind getting 3. And then I bet I could go even better. One thing I do want to highlight for you is that these calculations change depending on your function. So if I have y equals x squared, or f of x equals x squared, and I wanted the slope of the tangent line from 1 to 1.1, I would then substitute I would substitute in 1.14x, and I would square that. And if you square 1.1, do it in your calculator, you get 1.21. This number here is not magic. It comes from my function. So now I've got a slope of 2.1. And if you look at the last slides, I started with a slope of 5. Then I went to 4. Then I went to 3. Then I went to 2.1. I wonder if I could even go farther or close that interval. And of course I could. So I could go, this is the same slide again, I could go to 1.001. I just can't go from 1, 1 to 1, 1 because I get a 0 over 0 slope, which is undefined. So there is a trick to do this, and the one trick is to approximate it. It looks like it's approaching 2, so my guess is that the slope would be 2 or close to 2. But the trick is to use just a general notation. So a couple comments I want to make here. If I ask you to evaluate f of 0, that means I'm going to take a 0 and substitute it in for x. F of 1, how do I do that? Substitute 1 in for x. How about f of m? I substitute m in for x. This is the notation for evaluating the slope at 1. If I was evaluating the slope at 2, it would look like this. F of 2 plus h minus f of 2 all over h. Now I'm going to hit this a little bit more, but the thing I wanted to illustrate here that calculus students have a hard time with is finding f of 1 is no big deal. You substitute a 1 in there and you get 1 squared, which is 1. This is the tricky one. Oh my goodness, most students say, how do I do f of 1 plus h? Well, in place of x, you substitute a 1 plus h. The same way you plug an m in. In this case, you're plugging in kind of an expression. And we'll talk a little bit more about this soon. So here's the mathematics behind it. And I want to talk to you a little bit about h because this should look familiar in Intro to Calc. I believe it's called the difference quotient, and we'll call that the difference quotient too. You're probably used to f of x plus delta x minus f of x over x, something like that. I'm not really sure what letters they use in the Intro to Calc book, but you're probably more familiar with the delta x, but we're going to call that h. That's the way the calculus notation is in the course description. So if I substitute a 1 in, 1 squared is 1. Don't forget the function is y equals x squared. That's why I'm getting a 1 out, because I'm putting a 1 in and getting a 1 out. And then if I substitute 1 plus h in here, I get 1 plus h, but don't forget there's a square because my function is y equals x squared. If I FOIL this, I get this part, minus 1. And then I simplify this by canceling the 1's. I am then going to be able to take an h out of these two terms, factoring an h out, canceling the h's, and then I get 2 plus h. Now let me talk to you about what h is. H is a moment a little bit after 1. So you just don't know what this distance is right here. We're going to call it h. In the beginning, when we did this, we did the slope from 1, 1 to 4, 16. My h was 3 because it was 3 more after 1. 3 more after 1 is 1 plus 3, which would be 4. That's how I get the 4. And then I went all the way down to 1, 1 to 1.1, comma, 1.21. Well, my h here is going to be equal to 0.1 because it's 0.1 after 1. Now, if you think of this axis as time, like we did with the Wile E. Coyote jumping off the cliff, this would be from time 1 second to 0.1 seconds afterwards. What do we want to do? We want to shrink that interval down to nothing, so we apply a limit. This fixes the 0 over 0. If I substitute the 0 in originally, I get 1 minus 1, which is 0, and 0 in the bottom. with a direct substitution of a limit. You can't do that. So this algebraic simplification that all is done here, the purpose of that is so that I can plug in 0 now. Then I get 2. This is how you're going to calculate the slope of a tangent line. And that should look very familiar. I know they use the delta x here for h, but I will rarely use a delta x like you did last year. I will use an h, which means a little bit of a moment in time. This is extremely important. Pause the video if you need to, and write this down. This is how we find the slope of a curve or the slope of a tangent line. Couple little notations. This fraction here is called the difference quotient. And by the way, it is no different than this. That's the difference quotient. It's basically the slope, applying a limit so you can shrink the interval down to nothing with avoiding the 0 over 0 issue. That is your lesson on slopes of the tangent lines. We'll get into this and do a little bit more with it next class. This assignment here is all listed for you on Canvas. Do your best without me being in class to talk you through and to do some of the algebra. You're going to struggle with definitely some of these continuity problems. I only had you do, look on Canvas because I may edit this since you have time to work in class today. But Canvas is where you should really follow your assignment and the numbers you go through. But don't forget you have solutions to look up if you get stuck. And then, of course, the answers to lesson 2.1 and 2.2 I didn't get a chance to go over today, being gone. So I'll definitely go through all of these problems with you next class and answer any questions you have on lesson 2.1, 2.2, 2.3, and 2.4. Thank you very much. Good luck, and I'll see you soon.